An introduction to permutations and combinations. This is another way of saying this is an introduction to a subject called combinatorics. So that is a mathematical subject, and the details include counting, but it's not the counting that you're thinking of. It's not just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's counting in very sophisticated ways. Let's begin with a couple of examples. Suppose we want to choose 2 letters without replacement from the 5 letters A, B, C, D, and E. And of course, without replacement means once you pick the letter, you don't put it back in the bag, or you don't put it back in the drawing pile. So once you get the letter, you can only pick it once. How many ways can this be done if the order of the choices matter? So sometimes we want to count things with rankings, right? When you interview for a job, the employer is actually ranking you against a competitor. Okay, so a lot of times when we're trying to count something from a sample size, we actually want to rank those things. So let's do example A first. And we're going to do this with brute force. So what do I mean by that? Well, if you choose A, what else could you choose? You can certainly choose B. And you could choose A, C, A, D, and A, E. And remember, we're choosing 2 letters out of the 5. What if you chose B first? Well, then you could choose BA, BC, BD, and BE. And notice we are counting in a systematic fashion. So continuing with this pattern, the next one would be what? CA, CB, CD, CE, and then of course DA, DB, DC, DE, and then finally EA, EB, EC, and ED. And notice you have counted all the orderings of, choosing 2 from this sample size of 5. So altogether, how many possibilities are there? In other words, how many different permutations are there? We have 5 columns and, of course, 4 in each column. So there's 20 possibilities. Another way to look at this is look at the 2 positions. So let's say, if you wrote a blank space for the first pick, right? Let's say you want to rank number 1. How many choices are there for rank number 1? To rank it number 1, there are how many choices? There are actually 5 choices to choose from. A, B, C, D, or E. So notice there are 5 there. And then if you move over to the second position, how many choices do you have left to rank it number 2? How many choices do you have left to get number 2? So if you already chose A already, then there's 1, 2, 3, 4 choices, right? If you chose B already, there's 1, 2, 3, 4 choices. So notice you would put 4 here. And so to get all the possibilities, you would simply multiply this, and you get 5 times 4. Now, notice the numbers are counting down, and we do have a symbol for counting natural numbers going down and multiplying them together. What would that symbol be? Let's see. Why don't we try to write 5 times 4 in a very, very different manner. So we're going to write 5 times 4, which equals what? That is actually equal to 5 factorial divided by, let's say, some common factors here. It would be 5 minus 2 factorial. and that would do it. Notice that actually gets you 20. So in general, if you're counting permutations where the ordering of your possibilities matter, then we would write something like this. So out of a sample size of n, and you want to permute, let's say, r of those at a time, we simply write n factorial over parentheses n minus r factorial. And so there's a nice little formula for this type of counting. Now, when you see the word permutations, you want to remember that order matters. In other words, you are counting the orderings of your possibilities. And another way of thinking of order matters, think of it as ranking. What if order doesn't matter? Then we don't say we're counting a permutation. If an order doesn't matter, we say that we're just counting a combination. So let's start example B. And this time, we want to do this with the order not mattering. We start off in a similar way. We still count AB, AC, AD, and AE. But we no longer count BA. We only count what? BC. So if you look at example A, well, there's no reason to count BA because it's counted already here, AB. Remember, the order doesn't matter, so we're not counting all the different orderings. Continuing on, can we count BD? Yes, we can. And we'll count BE as well, because that is actually a new possibility. So compare this kind of counting with part A. Are we going to have more possibilities or less possibilities with combinations? So in part A, you're doing permutations. In part B, you're doing combinations. And which one has more possibilities? I'll let you think about it before the answer is finally revealed. I'm going to continue to count. Notice we don't count CA. We already counted that. So we could count CB, though. And we could count CD. And we could even count CE. Let me see here. CB. I lost my count. I apologize. We can't count CB. Let's try that again. We already counted CB. So we're going to what? CD and then CE. Oh yeah, that's much better. Finally, can we start counting something that starts with D? Well, we already have DA, we already have DB, we already have DC, so the only thing left is DE. There you go. And that's all the possibilities we have. Because notice E has been combined with everything as well. You could see it along the diagonal here. So those are all the possibilities. 4, 3, 2, 1. How much is that? That is exactly 10. Oh. So there are 10 choices in part B. And we are going to write 10 a little bit differently as well. So 10 here, we could write this as, let's say, 5 factorial over what? I'm going to do 5 minus 2 factorial. And then we're going to take off 3, well, sorry, not 5 minus 2. I meant 5 minus 3. That's a really important detail. Oh, wait. I'm going crazy. No. Stop it, Woo. I am saying 5 minus 2 factorial. Yes, that is correct. Yes. Now I'm going to divide out by 2 factorial. There we go. Like this. Yeah, that's it. And that really is 10. If you don't believe me, go ahead and compute that out. Here, I'll do it really quick. 5 times 4 times 3 factorial over 3 factorial, 2 factorial. The 3 factorials reduce, and then 20 divided by 2 is 10. And there it is. We have a notation for this. And the notation for this is actually, could write it this way. We could write n factorial over n minus r factorial times r factorial is equal to what we call, with a sample size of n, and we choose a combination of r of them. So we say this is written as, or read as, n choose r. Okay. If you're wondering how to read this one way to read this is say n permute r. Here we could read this as n choose r. And so with the C here, what you want to remember is that order doesn't matter and you're just counting combinations. So for part B, there were 10 choices. And for part A, there was 20 choices. Notice that for permutations, you could expect more possibilities, and combinations, you should expect less. The only other observation that I want you to make is right here, when we do this pattern for combinations, notice that you actually have all the permutations from the sample size of 5 taken 2 at a time. It's right here. Notice this right here matches with this right here. So you actually first count all the permutations and then you divide out all the double counts. And the way you make sure you don't double count is you divide by r factorial. So in this case, we are choosing two letters, so we divide by 2 factorial. And it just so happens that you removed all the extra counts, right? You wouldn't count ED again. You removed it, right? You wouldn't count EC again. You removed it. And you removed it by dividing this by the 2 factorial or the r factorial right there. So that's the introduction to permutations and combinations. Remember, for permutations, you're counting all the orderings. And then for combinations, the order doesn't matter.